Picture this. You're sitting on a bench in a quiet public park on a warm Tuesday afternoon. A woman walks over and sits down right next to you. Her skin is completely alabaster white, her hair is a shock of bright silver curls, and her eyes are two strikingly different shades, one vivid blue and one deep chestnut brown. Intrigued, you strike up a conversation and ask where her family is from. She smiles and explains that her family belongs to a tiny, isolated indigenous tribe deep in the Amazon basin, but she was born with complete albinism. As you keep talking, she pulls out a phone with her left hand, types out her contact info effortlessly, and tells you she remembers every single detail of what she was doing on this exact date 12 years ago, down to the exact weather and the breakfast she ate. You wake up 5 minutes later to your morning alarm, staring at the ceiling, heart pounding. It was all a dream, obviously. But as you pour your morning coffee, a genuinely fascinating thought pops into your head. Does someone like that actually exist somewhere on Earth right now? Statistically speaking, if you stacked up every rare genetic mutation, neurological quirk, and demographic statistical anomaly known to medical science, what would the single rarest human being on Earth actually look like? And what are the mathematical odds that a person like that could even exist among the 8 billion people alive today? To answer that, we have to build this hypothetical human from the ground up, trait by trait, using real global probability data. And the best place to start isn't with a genetic mutation, but with geography and human demographics. Right now, Earth is home to roughly 8 billion people, divided across roughly 7,000 distinct ethnic groups. But humanity isn't evenly distributed. If you picked a random human at random from a spinning globe, there's nearly an 18% chance they'd be Han Chinese. That single ethnic group accounts for more than 1.4 billion people. On the exact opposite end of the spectrum, you have isolated micro-ethnic populations. Think of the Sentinelese living on a remote island in the Indian Ocean, estimated at anywhere between 50 and 400 people. Or the Kawahiva in the deep Brazilian Amazon, with fewer than 30 surviving members. Or the Spinifex people in the Australian outback, whose population numbers just a few hundred. If we want our individual to be as statistically unique as possible from step one, we have to place their origin in one of these micro-ethnic communities. Let's use a conservative population size of 500 people. Out of 8 billion humans on Earth, 500 divided by 8 billion gives us a base probability of 1 in 16 million. Right out of the gate, our hypothetical human already has just a 0.000000625% chance of existing. Now let me layer on our first major genetic condition, complete oculocutaneous albinism. Albinism is a hereditary genetic condition caused by mutations in the specific genes responsible for producing melanin, the biological pigment that gives our skin, hair, and irises their natural color. In someone with complete albinism, the metabolic pathway that manufactures melanin is either severely impaired or shut down entirely. This results in pale white skin, silver or platinum hair, and light-sensitive irises that can range from pale blue to translucent pink, depending on how ambient light reflects off the unpigmented tissue. Globally, complete albinism occurs in roughly 1 out of every 20,000 births. Now, when you combine two independent statistical probabilities, you multiply them together. So, taking our micro-ethnic origin of 1 in 16 million and multiplying it by the 1 in 20,000 chance of albinism, our person's odds of existing drop instantly to 1 in 320 billion. To put that in perspective, that's already more than 40 times the entire population of planet Earth, and we've only picked 2 traits. Next up, let's look into their eyes. Green eyes are famously cited as the rarest standard eye color, appearing in only about 2% of the global population, or roughly 1 in 50 people. But green eyes aren't a genetic mutation. They're just a specific mix of low melanin and Rayleigh light scattering. If we want a true statistical anomaly, we look at complete heterochromia. This is a rare condition where a person possesses 2 entirely different iris colors. For instance, 1 bright blue eye and 1 rich hazel or brown eye. Complete heterochromia occurs when melanin distribution during early embryonic development is asymmetrical across the 2 eyes. In the vast majority of cases, it's completely harmless and doesn't affect vision quality at all. Medical literature estimates that complete heterochromia occurs in roughly 0.06% of the global population, or about 1 in every 1,667 people. When we layer complete heterochromia onto our person, their mathematical odds plunge to 1 in 533 trillion. Now let's talk about motor control and motor lateralization, specifically handedness. About 90% of the human population is right-handed, making natural left-handedness a 10% minority, or 1 in 10 people. But here's where it gets interesting. Handedness isn't just a simple habit you pick up in kindergarten. It's tied directly to brain lateralization, how your brain divides up complex tasks between its left and right hemispheres. For most right-handed individuals, language processing happens almost exclusively in the left hemisphere of the brain. In left-handed individuals, however, language and spatial processing are far more distributed across both hemispheres. Even identical twins, who share 100% of their genetic code, differ in handedness about 20% of the time, proving that hand dominance is a mix of complex genetic markers and prenatal development factors. So factoring in left-handedness, a 1 in 10 chance, our person's combined probability shifts to 1 in 5.33 quadrillion. That's a 5 followed by 15 zeros. But we aren't anywhere near done yet. What if our person sees the world in a way almost nobody else can? Most humans are trichromats. We have 3 distinct types of cone photoreceptors in our retinas, tuned roughly to short, medium, and long wavelengths of light, or blue, green, and red. Our brains take the signals from those 3 cone channels and blend them together to perceive roughly 1 million distinct shades and hues. But a tiny fraction of humanity possesses a 4th cone cell sensitive to wavelengths right between red and green. This condition is called functional tetrachromacy. A functional tetrachromat doesn't just see bright colors. They can distinguish subtle chromatic variations that look identical to the rest of us, expanding their visual spectrum from 1 million colors up to an incredible 100 million colors. Functional tetrachromacy is almost exclusively found in women because the genes for red and green cone pigments sit on the X chromosome. A woman can inherit 2 different versions of the gene, one on each X chromosome, potentially creating a functional 4th cone type, whereas men only have a single X chromosome. Researchers estimate that while up to 12% of women carry the genetic mutation for a 4th cone, only a tiny fraction actually develop functional tetrachromacy, roughly 1 in 40,000 women, or 1 in 80,000 people across the total global population. Adding functional tetrachromacy drops our humans' odds of existing to 1 in 426 quintillion. Finally, let's give our subject a neurological superpower that deals with memory. Hyperthymesia, officially known as highly superior autobiographical memory, or HaSHM. People with HaSHM possess an extraordinary, almost eerie capacity to recall virtually every single day of their lives in vivid detail. If you ask a person with HaSHM what they were doing on a random Tuesday 20 years ago, they won't just tell you the date. They can describe the weather, what they wore, the exact conversation they had over lunch, and what news stories were playing on TV, all without consciously trying to memorize it. The condition was first formally documented in 2006 by neuroscientists studying a woman named Jill Price, who described her memory as a non-stop, continuous, involuntary movie running in her head. To this day, researchers have confirmed fewer than 100 genuine cases of HaSHM worldwide. Even if we're generous and assume there are hundreds of undiagnosed cases living quietly around the world, let's estimate a total global presence of 500 individuals. That gives HaSHM a probability of 500 out of 8 billion, or 1 in 16 million people. Now let's do the ultimate math. When we combine a micro-ethnic population of 500 people, complete albinism, complete heterochromia, left-handedness, functional tetrachromacy, and hyperthymesia into one single human being, the stacked probability comes out to roughly 1 in 6.83 septillion. That's a 6 followed by 24 zeros. To help your brain wrap itself around a number that absurdly huge, consider this. Astronomers estimate that the total number of stars in the entire observable universe is around 1 septillion. If you gathered every single grain of sand on every beach, ocean floor, and desert across the entire planet Earth, you would need to combine the sand from nearly 1 million Earths just to reach 6.83 septillion grains. And here's the wild part. We didn't even include rare blood types like Rh null, extreme height anomalies, hyperflexibility, or rare cardiac mutations. The mathematical odds of this exact individual walking Earth right now are functionally 0. But this mind-boggling math highlights something deeply profound about human biology. You don't need a list of medical mutations to be statistically miraculous. The unique combination of parental genes, neural wiring, physical traits, and personal memories that make up your specific life represents a 1 in trillions roll of the cosmic dice. There may be 8 billion people swimming in the human gene pool today, but not a single one of them processes the world quite like you do.